Jaden, we're live.
Kip, hello there,
Hello,
and welcome everybody else.
welcome.
This is our second
Number
lesson.
two.
Uh, Number two. Our first lesson, we went over reference frames and what a function is. So if you missed that, go check it out. Uh, Today we are going over slopes, limits, derivatives, and that leads us to velocity and acceleration.
Yeah, it's definitely a lot to take in today. So hopefully we get through it all. If not, we'll probably have to push a little bit to next week, but I think we'll get through it all. But it is a lot. And these concepts
Yeah,
are things that are going to blow your minds. Right, Jaden?
yeah, and hopefully, if you've heard of some of these things, by the end of this lesson, hopefully they'll make sense. Uh, just a little bit more than they did before.
Yeah.
That's all we're asking, right?
Yep. By the end of this, you guys will all be super smart and know calculus. So you can tell your friends, guess what? I know calculus now. So if you've never
Yeah,
taken a
and then
calculus class, you will now know all the fundamentals. Well, half of the fundamentals. Next week we'll be we'll be doing the other half.
yes. Um, all right, so Kip, we have to start us off, we have this review question,
Yeah.
right? Uh, it's meant to be somewhat simple, also somewhat leading into our next slides, right?
Yeah.
So our question is write a function. So we should all know what functions are because we were present last week and we know that. Okay.
Okay.
So write a function for the displacement of a ball that travels 60 miles every hour. Okay. Um, how should we start this, Skip?
Well, Jaden, I think the first thing we need to do is so it says I like to just kind of write it out. So with word problems, which
Right.
is something that a lot of people I think get scared about when they see things written out with words. Um, but I like to just kind of break it apart and write down the things that we know and maybe the things that we um, need to, or what we need to solve for, right? So it sounds like we're writing a function for the displacement. So I'm going to go ahead and write a d here for displacement. And it's going to be a function, so I'm going to go like this. Boop, boop. And so it's going to be d of something, right?
Right.
And then I'm going to keep reading here, and it says of a ball that travels 60 miles every hour. So if it's traveling at 60 miles every hour, that sounds like a constant to me, right? That value is not changing. So I need to
Right.
figure out what my independent variable is. But it sounds like the displacement is probably going to be changing with time, right, Jaden? Would you agree with me on that? Because it's traveling
Yeah.
60 miles every hour. So every hour later, it's probably going to be 60 miles further away, right? So
Right.
I'm going to say that it's going to be a function of t for time. And that's going to equal
Okay.
something. Now, Jaden, do you want to take over from there?
Yeah. So what Kip has written so far, that's most of the time you'll see functions written this way, right? D of some variable. In this situation, right, we have this number 60 miles every hour. So we're going to use, we know we're going to have a T on this side symbolizing our time, right? And then if it's 60 miles every hour, that will be multiplication, right? So I'm going to just write 60t. Okay. Is there anything else that needs to be included in this equation, Kip?
I don't think so because we don't have a start placement or anything like that, right? And so I think we
Right.
have written out a function that describes this statement. By the way, if you
Right.
guys remember last week, I gave you guys a little homework assignment telling you guys to think of things that in your daily life were functions, right? So if you want to go ahead and put in the, chat things that you guys found in the last week that are functions, please go ahead and do so. Um,
Right.
and while you're at it, don't
Okay.
forget to hit like and subscribe if you haven't already.
Right. One thing I want to just add real
Yeah,
quick with this function that we've written down, our t will be in hours, right? That will be an important part. Obviously, we could convert it to seconds or minutes, but for this function, there's no need to. So I just wanted to point that out.
yeah, and I think we
Okay.
actually got a question just kind of specifically about that. That said not necessarily to put in per hour. So yeah, we're stating that our t is equal to hours. So that's our unit for that. Um, so thank you for that question. Kelsey, we already went over vending machines last week. That doesn't count. That was the
I'm
example.
glad.
I'm glad you remember, but that was the homework was to find other things besides vending machines that work like functions.
All right.
Alrighty.
Um, Now we're going to move on to the slope. Okay, this is important for derivatives, and you'll see why in just a little bit. But the slope is the rate in which the dependent variable changes compared to the independent variable, right? And oftentimes you'll hear slope as the rise over the run, right? The rise being the up and down change over the left and right change, right? That'd be the run. Sometimes you'll see it as we have it written on our slides, the delta y divided by delta x. That triangle is the delta. That just means the change in, and the change is a subtraction problem, right, kids?
Right.
So we got to keep that. We got to remember that change in something is subtraction, and that's basically what the slope is, right? Two subtraction problems, and you just divide it, right?
Right. Should we go maybe write that out on the Jamboard real quick? Um,
Yeah, we can do that.
maybe we need to add
What page?
I think we might need to add a second one and just add one. Go for it.
Right.
Or do you want me to add? I don't care. By the way, I was laughing not at you. I was laughing because we got a comment saying that um, the I already added one. I'm ahead of you. All right, but now it won't go away.
Oh,
Go away.
good job.
But it said the vending machines are the only one. So apparently, vending machines are the only thing in our world that are a function. Even though we just proved that wrong because our question that we just asked was, our review question was another thing that is a function.
Right. Okay. So are we on slide
Yeah,
2
we're
right
on
now?
slide 2.
All right. So the delta, right? That's just a triangle.
Yeah,
Looks like a triangle.
right.
Oh, you.
There you go.
So we have delta y over delta x. So this is equal to, if we have two y values, y2 minus y1 over x2 minus x1, right? I was saying earlier, the change is just a subtraction problem. These little subscripts just mean there are two different y values, right? It could be 5 and 3. So that change would be 5 minus 3, which would be
2.
2. Yes. And then your x values could be something similar, 4 and 3. So it'd be 4 minus 3.
1.
And that would be yes. Okay, so our slope in this case would be 2 over 1, which is just equal to 2. Okay, so you can have fractions of like 1 over 2.
Whoops,
It could
Jaden,
be
they
whole
see it. I
numbers.
forgot to switch to the right screen. Now they can see it.
Oh, perfect.
Sorry,
Okay.
people.
So that's the slope, and that is very important for derivatives, and you will see in several minutes. Okay. Do we need to add anything else for that, Kip?
No, I think we're okay. But if you guys don't fully understand what slope is, please comment now, because it is going to be very, very important for the things we are about to go over. So if we didn't explain something clear enough to you guys, I know for most of you this should be a review, but if you have any questions on this specific thing, please ask questions now because it will become very important later. Okay.
Right.
So Jaden, after we go through slope, we get to limits. What on earth is a limit?
So limits are useful for functions that don't really give you a clear answer, right? So limits, as we have written down, it's a function that you need to approach it to something. And you might be asking, like, what the heck does that mean? And yeah, what the heck does that mean, Kip?
That's a good question, Jaden. Yeah, so it means, so for example, I'm going to play a video here in a second that will hopefully kind of clarify this idea. But what it means is, let's say, Jaden, I want to walk and get closer to Jaden, right? But every time I take a step, I go half the distance. And so, you know, I start at a half, or I start at like one distance away, and then I go a half and a quarter, and so on. I know I will eventually reach you, right? But mathematically, I never actually will if I keep breaking it up by half. And so that's what it means by approaching. We know that that distance will eventually touch, but kind of from a mathematical standpoint, it's kind of weird. And so I'm going to show kind of a similar video talking about that right now. And it has to do with circles. Ready? So here we go. So it says r equals 1, r equals 1/2. So this is the radius of the circle, right? And it keeps getting smaller and smaller. And we'll play it again for you. But the thing is that this radius will never actually get to 0, right? So it keeps halving over and over. But if we take the limit of that function, right?
Right.
As the radius gets smaller and smaller, it will eventually equal 0, even though maybe mathematically that doesn't work.
So in that situation, right, we would say the limit of this function as x approaches infinity, right? Because we would go on forever in this situation. And we're saying as we go on and on and on and on, our function gets closer and closer and closer and closer to the value 0, right? Mathematically, that would never happen, right? Because we have infinite numbers and we can go infinite decimal places, right?
Mm-hmm.
But as we take the limit, we get this answer of 0. And that is very important for derivatives.
Yeah.
Because we'll want to cut these functions up infinitely, some cases, right, to describe a certain point on that function.
Right, and Jen, that's... Okay. What the heck? Why did it not work? Jen, it's mathematical. There, now it goes.
Yes, it
So
is.
do you want to talk about this kind of weird, funky formula we got here that says limit, and then underneath it, it's got an x with an arrow of a, and
Yeah. So when we are writing the limits out, you'll see this lim and then fx, right? F of x, and then the x approaches, that little arrow symbolizes the approaches. And a just represents some value that we want to see what this function looks like around that value. Okay, it could be 0, could be 1, it could be infinity, right? But we want to see what happens to this function as it approaches a certain value. And then it says equals L, and that just represents that equals the limit, right? And then this bottom part, if and only if, it's saying you can take the limit as it approaches from the positive direction or the negatives, right? So if we have two directions approaching, what happens then? And if they both equal the same thing, that means it's the true limit, I guess. Like,
cool.
is that kind
Yeah,
of,
no, that's good. Thanks, Jaden. Um,
yeah.
so I'm wondering, because of the importance of understanding limits, if we want to go to the Jamboard on that same slide and just kind of use that example of 1 over 2 to the x and just kind of write
Yeah.
some out and kind of show, you know, what
Yeah, let's do it.
what happens there. Um,
You stay still on slide 2.
yeah, so if we've got, 1 over x or 2 to the x, right? And so if we say, and this equals f of x, look, Jaden, it's a function.
Whoa,
Whoa!
that's awesome.
So let's start plugging in numbers. So let's say f of 0, okay? And that's going to
Okay.
equal 1 over 2 to the 0, which is going to equal 1, right? And if we go f of,
0 power equals 1, just for people
yeah,
that don't remember that.
f to the 1 equals 1 over 2 to the 1, which equals 1/2. And if we
Yep.
go f to the 2, this is going to equal 1 over 2 to the 2, which equals 1 over 4. And so on and so forth, right? And so we can see, let's plug in some
So
huge number. If we plug in f, well, 1 over 2 to the 100, and I have no idea what that is.
that number is going to be very, very, very small.
Yeah. And so we see that that number is going to be really, really small, right? And so we can write this and say the limit of um, the limit
1 over 2.
of 1 over 2 to the x as x approaches infinity equals 0.
Yes.
Yeah.
Yep. So what Kip was showing with writing out a couple of these actual like input values is we'll never actually get 0 as an answer, right? But when we take the limit as x approaches infinity or x goes to infinity, right, we get this limit to equal 0. And that is the important part for like that having the circles, right? Because eventually it's not going to be anything, but that's why we need this limit, right?
Right.
And that example of you walking towards me, right? That it's you're going to reach me at some point, but mathematically we'll never get that 0 value.
Right. And so I like to, so the limit basically makes it possible to get 0. Yeah, I mean it's and the way I think about it is it's like this kind of breakdown of real world situations versus the mathematical world, right? In math, we're perfectly happy with using infinities and all this kind of stuff that in the real world we just are like, no, that's not there. That's kind of
Yeah.
how I think of it. Um,
Yeah.
so Kelsey's response is even if it's not technically possible. Um, it this is the weird part, right, Jaden? I mean, it is technically possible eventually, right? It happens
Yeah.
at the point infinity. Um, but
Yeah.
what is infinity? I mean, that's like a whole philosophical debate at that point,
Yeah,
you know?
there's different kinds of infinity too.
Yeah.
So it's
So it is technically possible, but just if you look at it from a purely mathematical standpoint, it would maybe not be possible, but it is, and so that's where this.
well, it's possible because we have discovered these limits,
Right,
right? That's the whole point mathematically for the limit, right? Because they're like, crap, this doesn't happen if we keep writing out these problems over and over and over. But it happens because we see it in real life, right? We
right,
see this person having these distances, but eventually reaching where they want to go, right? Or passing someone else, right? So that's why we have these
yeah.
limits.
And it'll make a little more sense, I think, when we get into velocity and acceleration and talking about it and talking about, because I have a specific example using, frames per second, how cameras work, and kind of this idea that as you, um, you know, it eventually becomes, the frames per second look continuous to your eyes. So, yeah. All right.
Right.
Let's move on to the next part of our lesson, Jaden, shall we?
Okay. And that is derivatives, right? We've already watched the video of the circle, right?
Yep. I'm
So
trying to get
we're on
through it here. There we go. Okay. All right, now we're on to derivatives.
okay. So what a derivative is, it is the instantaneous slope. So we just learned about slope, right? It was the rise over the run or the change of y over the change in x. Okay. So the derivative is the slope at a certain point of a function, right? Because all of our, or I guess not all of the functions, but a lot of functions are curvy. Okay. So it's hard to get that line, right? But that's what the derivative helps us with. And that is the slope of the tangent line at the given point. So the tangent line, if you have these curves, right, you just draw a straight line and you touch the curve at one single point. Okay? And that would be the tangent line at that point. And that is called the derivative. So that's what we're looking for. Okay, so the slope at certain points on
Right.
our functions.
So it's essentially, right, when we're looking at, we take this slope, right, but we're almost kind of, we're breaking it up into such small, tiny sections, right, that we're getting this
Yep.
little tiny rise over this little tiny run.
Yep.
This little change in y over a little change in x, and that equals the derivative. It's the instantaneous slope. It's the tangent line at a given point.
Yeah.
So yeah, it's just
And that's
think
why,
think little tiny increments.
yep. And that's why those limits were so important, right?
Yeah,
This allows us to get it so small that it's at a given point.
right.
It gives us a slope. Okay.
Okay.
Um, and that leads us to the definition of
Yikes,
derivative.
Jaden, that looks scary.
Yikes, you are wrong, Kip. It's not that scary. Okay.
There's a whole
So,
bunch of letters, Jaden. I see one number. I see a 0 on that slide, and that's it.
right. So, what Kip was just looking at, uh, let's say we cover up this f prime a equals lim part, right? And if we only have the second part, so after the limit, we have a change of something over a change of something else, right? We have a subtraction problem on the top, subtraction problem on the bottom, and
This one down
if
here.
you,
Woo. Yeah. Okay.
yeah, if you recall, we said that oftentimes we represent functions with like the f, then parentheses, and some other letter. This would symbolize our change in y, right? The f of x would be like our y2, and the f of a would be y1.
Ah,
Okay, so
Y1. Yeah.
that's our change in y in the numerator. Okay, and then same thing with the denominator is we have an x minus another value, so another x value. We'd have an x2 minus x1, and that is also just the change in x. And the little limit part tells us we're just getting really, really small, right? Kind of what you were explaining on that last slide, Kip, is we just take this limit of a very small portion and we get the derivative using the change of y over the change in x.
Right.
Same thinking, just at a smaller scale.
Yeah. So we have a comment saying, can you draw a picture of a curve with a tangent line? And I think we should go ahead and do that with the Jamboard on this slide. And also and we can show kind of that tiny change over that tiny change. You down for that?
Okay. Yeah, for sure.
Cool.
You said slide, which one?
I think it's slide 3 now.
Okay.
Okay.
All right. So if we have,
nice
okay.
line.
I don't know what happened there. It almost looks like negative x cubed though. Pretty cool.
You did good.
Okay. Let's, I don't know, let's just draw a curve like this. Okay. So let's say our function looks something like this. That line can go on forever, that one too. Okay. And let's say we want to take the derivative at this point right here. Okay.
Okay.
Our tangent line, is there a tool on here to draw perfect lines? Okay.
Maybe the shape, is there, I don't know. No, you can do a little tiny rectangle.
I guess. Okay.
I don't know.
So our tangent line, oh, that's not going to work.
Here, I'll draw it in for you.
Okay.
Let's see here. Okay.
So our tangent line touches at that point. You see how Kip has drawn us a wonderful line.
Just right there.
Okay, so that's what the tangent line looks like. And then showing the small increments, we can, I feel like we need to like zoom in at that section. So let's zoom in over here. So there's the line. It's touching the curve like that. Okay, so our limit works how I picture it is just getting smaller and smaller sections until you're satisfied with how much you want to go with.
Yeah.
Okay, does that kind of sound right to you?
Yeah,
So
I mean,
at first, it off in big chunks like this, right?
right.
Those are obviously too big for what we need, so we make them smaller, right? Make the section smaller, and this goes with the horizontal direction also. Okay, so eventually we're going to get, let's say, this tiny box that we've got over here, and it has sections here, 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 here. So And if we zoom in more and more, we get this section off smaller and smaller. And this could be, for example, our x1 and then our x2 at these two lines, okay? And then same with our y, y2, y1, okay? So as we get smaller and smaller to this certain point that we are trying to take the derivative of, we get this smaller and smaller subtraction problem, and that gives us the slope.
Right.
Uh,
So just, and
and
yeah, so, you've got this x1 and x2, so we could say, according to, our definition over here,
yeah,
we could say that x1, right, is going to equal x, and then our x2 equals
yeah,
a, right? And the whole thing with this upper part of the limit, or this upper definition, it says as the limit goes to 0, right? So that says the distance between those 2 points, or this is supposed to be an h in here, not an x. But it's supposed to be as, those 2 points get to the point where they're essentially on top of each other, right? So x1 is so close to x2 that they almost equal each other. They don't quite equal each other, but
yeah,
they essentially do, right? Just like as I get closer to Jaden, I'll never actually touch Jaden, even though I will.
yeah.
So,
It's yeah. Uh, Let us know if we need to talk a little bit more about this. Um, yeah, just let us know.
yeah, I think hopefully it will make a little more sense as we go into our examples using velocity and acceleration. So we have little neater graphs and stuff set up, so hopefully it will make things make a little more sense here.
Yes.
Because I was telling Jaden before we started this that calculus didn't make a lot of sense to me until I started learning physics and actually had real world applications of this alphabet soup that we've got in front of us here. So,
Yes.
but, alrighty, so let's move to the next slide. Ooh, velocity, Jaden. So,
Okay.
velocity is something you guys have probably heard a lot about. You've probably heard of it more in terms of speed. Um, but speed is the magnitude, and velocity is a vector. Vector just meaning that it has a speed and also a direction at the same time, right? So if you're going west at 60 miles an hour, that's a velocity. If it was just 60 miles an hour, that would just be, oh, whoops, thank you for reminding me. I was still on the Jamboard. Um, so, yeah, sure, Andrew. Zeno's paradox of the arrow. Jaden, do you know that one? I don't know that one. But I'm assuming it's
Sure.
probably similar to your rabbit. But Andrew,
So,
please enlighten us. I'd love to know more. Um, Okay, so we've got velocity. So 60 miles an hour is speed. 60 miles an hour to the west would be a velocity. All right, so it's both direction and the speed. Um,
yeah.
so I like to think as speed or velocity as the change of displacement over the change of time. Jaden, that sounds awfully similar to what? What kind of math that we just talked about?
That kind of sounds like the slope.
The slope.
Yeah.
Awesome.
Crazy how this all like lines up with each other,
That's
you
weird,
know?
man. It's like we planned this out beforehand and chose topics that all work together. Um,
Yeah.
so um, the slope of displacement, right? The slope of our function of displacement is actually going to be our velocity. because it's the change in displacement over the change in time, okay? And the units for it are simply just the distance divided by a time, right? Which makes sense if you've got a displacement, change in displacement over change in time, you're doing division. And so, yeah, it makes perfect sense that that's the units. Now, the last part about velocity that is important is it is the first derivative of displacement, right? So,
Kip, what do you mean by first derivative?
so Jaden, remember how we were just talking about those derivatives,
Yeah.
the slide before? So you don't just have to take a derivative one time. You can keep taking them as many times as you want.
Really?
As many times as you want. So a first derivative is the first time you did it, you took that derivative of a function, okay? Just the same way, like you can divide by 3 over and over and over, right? You can divide a number by 3 and 3 divided by 3. Same thing with derivative. We can take the derivative of displacement more than once. So it's the first derivative, right?
Okay.
Because and the reason behind that is if we want to find the instantaneous velocity, right? Let's say that we have this displacement function, but let's say the velocity isn't constant throughout the whole thing, and we want to find an instantaneous velocity, then we want to find the instantaneous slope, right? Which is the derivative. Okay. Okay, so I'm going to go ahead and we're going to have some fun here now. Watching some animations. Not this one. We already watched that one. So we'll let that one go away wherever it is. There it is. Okay, so the first one I'm going to talk about. All right, so what's happening is I've changed the frame rate, right, of the camera for each of these videos. And so a way to think about it is a camera has a frame rate. It's how quickly it can look at pictures, right? Or how quickly it can take a picture, and a video is just a whole bunch of moving pictures. So from our standpoint, it's like, okay, if we watched this ball move and then looked away and then looked at where it was again, and we get something that looks like this. So if we keep looking away and then looking at it, and this is 1 frame per second, I believe, we get this line appearing on the graph, right? And if we go to the Jamboard now, and we go to the next slide, and we go ahead and switch things up here. So we've got this graph, right? And it's like every second I looked back and saw where the ball's position was, right? And I plotted those points on a graph. And we see we get these dotted lines, right? So at time equals 0, it's at 0. At time equals 1, the displacement is 1, and so on and so forth, right? And so we can go ahead and we can draw a line in between these. Boop. Cha-ching. Whoa. And we could go ahead and find the slope of this, right? And so we do that by, finding our rise over run. And so we could go ahead and say that, we've got at some random point here, we could say y is, we could say y2 is equal to 3 and y1 is equal to 2, right? So we've got, right, yeah, 1, so this is 2 and this is 3, right? And so we can go ahead and say that it's going to be 3 minus 2 And then on bottom, which is a run, right, going along the x-axis here, we also are going to have a x2 is going to equal 3. And, sorry, x1 is going to equal 2. So we get another 3 minus 2. So we get a 1 divided by 1. And that means that our velocity, right, between those time frames, or between, you know, t equals 2 and t equals 3, our velocity is going to equal 1. Well, this is a straight line, so that means that it has a constant velocity because the slope is not changing, right? And so if we drew out a velocity graph now, boop, boop, and we make this v of t and this t, we would just get a flat line at 1, right? And that's due to the fact that this is constant. So if we go ahead and we can we'll watch that one again, right? So boop, 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 boop. So what happens when we increase, what happens when we, boop, boop, boop. What happens when we double the frame rate? So now we have, 2 frames a second. And we watch it again. Here we go. So we notice that there's now more dots popping up, right? And that ball behind the graph is actually, it looks like it's moving more fluidly, right?
Right.
And so I'm actually not going to say that this graph is what we said it was here. I mean, it is, but yeah, we'll leave it as is. Okay, so that's like that. So now I'm going to go back to our Jamboard and move to the next scene over. And look, Jaden, we have this same line, right?
Yeah, has a little bit more dots on it now.
Has a little more dots on it, but we could still choose the same 2 points, right? We could still choose equals y2 equals 3 and y1 equals 2. And same with our x, right? And we'd still get our velocity equals 1.
Right.
So now we're going to go a little further, okay? And we're going to watch it again, this one, and then we'll watch another one at 30 frames a second. Okay, so this is where this idea of the limits start to break down, right? So we're looking away, we're looking back, we're looking away, looking back.
We're just going.
But we're going to start going really, really fast, right? To the point where our eyes perceive it as continuous motion, right? Our eyes can see things about at 24 frames a second or 30 frames a second, somewhere in there. So we're going to go to 30 frames a second, and this ball, to everyone watching, is going to appear as if it is just moving continuously, right? That it's not choppy at all, even though it actually still is. So, here we go. So again, that ball is still moving little tiny increments.
Right. But to us, it just looks like a solid line.
Right. Exactly. And the other thing that's important to remember, if we go back to our board, is we could take any 2 points on any of these graphs and it will give us the same slope because it is a straight line, right? And so, even if we, on this graph where we've got these little tiny, tiny changes between it to the where you can't even tell where 2 different balls are, you could actually take that and calculate the slope between those 2 little tiny points, and you would get that the slope was still 1.
Okay.
So is that making sense so far what velocity is to people? If it's not, please let us know. Um, and then we're going to go ahead and move on to acceleration now. Wait, I got to do some stuff here. Hold on. All right. So now we're on to acceleration. So the acceleration is the change in velocity over the change in time. Jaden, what does that sound like again?
Kip, that sounds like we're going to take the derivative of velocity to get the acceleration, right? It's just a
Exactly.
slope.
Yeah. What? That's crazy, right?
That's
So,
mathematical, dude.
dude, you think so?
Yeah, it is.
Okay, dude, it totally is. So that's what acceleration is. Now people have heard acceleration before. You know, they always use it as like a car statistic, um, saying that
0,
what?
2 seconds.
Yeah,
Or
0 or 0 to 60 in 2 seconds, right? Like they always use that to determine it. And so that's how quickly it changes from going 0 miles an hour to 60 miles an hour, right? So its acceleration would be that 60 divided by 2 times, you have to convert it to hours,
yeah.
which is going to be 2 divided by 3,600, right? I
Yeah.
think so. Um, and you could actually figure out what the acceleration of that car was. I'm not sure when I'm adding a unicorn to that animation. Someday soon, hopefully.
Just right in the rainbow.
Yeah,
Would be pretty amazing.
it would be pretty amazing. Okay. Um, so here's the deal. The units for it are just going to be distance divided by time squared, right? Because velocity, we remember, is distance divided by time, and so we have a distance divided by time again. So it becomes distance divided by time squared, okay? And Jaden, like you pointed out, it is a derivative. It is the first derivative of velocity. But what's the derivative, or what's velocity a derivative of?
The first derivative of displacement.
So, therefore, acceleration is the second derivative of displacement.
Oh, it's not the first derivative of the first derivative of velocity?
No.
I don't know.
Okay.
So the second derivative. Cool.
Cool. So now we're going to go back and we're going to watch some more videos with that lovely ball. We're going to name him Bluey the Ball. I don't know. He's probably going to hang out with us for a long time.
Yes.
But we're going to go back to the ball here. We're going to watch that one again to show you a constant velocity, right? This is constant. Now, Jaden, what happens when this ball starts to accelerate? But we're going to start with only, 1 frame per second again, right? So we're going to look away, look back, look at it again, look away, and we're going to see what happens to this ball.
Right.
So it's kind of hard to tell in this first video, right? But the ball is speeding
Yeah,
up.
spaced out. It sort of looks like a line, but maybe a little bit of a curve at the beginning. I don't know.
Yeah. So we can go ahead and let's go to the Jamboard now. Hop on
Yeah.
over.
Zoop.
Zoop. And let's go ahead and look at that graph. Okay. So, Jaden, let's say that we wanted to take the slope, right? Before, it didn't matter where we took the slope of the line, it was always going to be the same. But let's say we want to find this starting point here and go to here to find our velocity, right? So we're going to find that. So y2 is going to equal,
That 5?
that's 5, yep, and y1 is going to equal 0, and x2 equals 5, x1 equals 0, okay? And so if we go ahead and we find that slope, we'll get 1, right? Is that right?
Yes.
Yeah. Hey, look, that's
5
the
minus
same as
square root over
before,
5.
right?
Whoa! It's the same function, dude.
Dude, you think?
Yeah, it has to be. We took the slope.
Okay, but Jaden, what happens if I check this slope right here?
Okay,
Ah,
we can try it. It's still going to be the same.
dude, I don't know. Just look at that line. That line looks way different than the other line, don't you think?
Well, that's just your graphing skills.
No, dude, my graph is spot on. I used math to calculate it.
Okay, maybe you're right. Let's calculate it.
Okay, well, before we do that, what we found by doing this, that first line, is we actually found the average velocity, okay? So this is the average velocity across the whole time span. But let's say now that we want to, find it in between. I don't get that comment. But well, okay, so we're running out of time here, but so if we wanted to find though the slope between this point, right, we could do that, or we could find the slope between this point here, and we could find the slope here, and we could find the slope here.
Whoa, Kip, those all look different.
That's because they are all different. Because Jaden, remember, velocity is the slope of displacement, right? And so if this ball is accelerating,
So right now you're kind of doing what we were talking about, breaking it up into different sections, taking the derivative. Okay, this is all coming together now, Kip.
you think?
Also, that kind of looks like a mouth, with teeth.
Ah.
But
Okay, so there, but right now, Jaden, right, what we're finding is we're not finding the instantaneous velocity, right? These are all going to be average velocities between those 2 points. So if we looked at a graph, if we looked at our velocity graph, it would kind of look something like this. We'd get this kind of stepping effect, right? Where it'd go like this, where our v between those time frames would be the same, and it would step up and step up and step up because we'd be getting all these different average velocities.
okay,
So now
let's
let's watch that video again, and we'll watch another one to give us reference. So remember, this is every second we're looking at this, okay? So now let's look at it every 2 seconds. Where are you? Right here. So now we're getting more of these points, right? And we still haven't found the acceleration, and we're getting to that, right? So if we go ahead and go back to our Jamboard now and move on to the next slide, again, we can take this slope from the first point to the last point, and that's still going to equal 1, right? And that's our average. But Jaden, notice what happens here if we take the slopes. Again, we get these smaller slopes appearing, right? And if we were to go
add them
ahead,
all together.
if we were to go ahead and write this on a graph for velocity again, we would get something that looked like this. It'd be shorter lines, right? Stepping up. So we'd get these shorter lines of it stepping up, and they'd be closer and closer together. So we'd have more lines in between each line, okay?
Yep.
And now, Jaden, we're gonna go back. We're gonna watch it
Starting to become
at
a line.
what? Yeah, it's starting to look like a line, right? It's getting closer and closer to
Yeah.
looking like a line.
Yeah.
So now we're gonna go back to the 30 frames a second, right? This continuous motion, and let's take a look at it. And now you can actually watch that ball in the background. It's speeding up, right? Let's watch that again. It speeds up. And as we can see on our graph, we get this kind of curving shape that starts to appear, right?
Oh yeah.
And so let's go ahead and get back to this curve, right? And so now, Jaden, again, we can break these little tiny pieces up, right?
Yeah.
And we could find the little velocities in between there. And now, if we draw this graph, v of t, what we'd actually get is we would get a graph that looks like this. It'll become a straight line if once we hit that, that continuous point, right?
Yeah.
So we
It's
take a
awesome.
slope and, say at a point here, right? And it would be the tangent line, and that would be our derivative, right? But notice that that line, no matter where we take it, is going to be slightly different, right?
Yeah.
It's changing no matter what point we're at.
It would look almost horizontal.
Right. And so now, Jaden, we have an acceleration graph. We're going to go a step further, right? So we have this velocity graph. And what happens if we know that this is a straight line, and we know this because I'm the one that wrote the function for the displacement.
Yeah.
But if we took any 2 points in between here, we would get a constant slope. And for this one,
Right.
I know it's going to be 2. So our acceleration
Okay.
will just be constant at 2. It will be a flat line. And that is derivatives, acceleration, velocity, all in one nicely knit together thing. And if we want to, we're kind of running out of time, but we could take the derivative using I think we should go ahead and do it. Let's take
do it.
the two derivatives using that equation. So I'm going to go ahead and write out, I'm going to do a new slide, okay? And I'm going to tell us what the function was that I graphed here. I'm going to set the background to black. How'd you know?
Dude, I don't know. Math wizard over here.
D of t is going to equal t squared, all right?
Okay.
Okay. Do you want to take this, Jaden? You got this, dude.
Sure. So we have d prime of t equals the limit. Should we do the bottom one or the top one, or either?
I think a mixture of the two.
Okay. Let's say.
I don't know. As x goes to as h goes to 0, let's do that one. Yeah.
H goes to 0. Okay. Okay. So now we have f of a plus h. So what does that mean, Kip?
Did you write it down? F of a plus h?
Oh, no, I didn't write that part down.
Oh, okay. So
saying,
f of, yeah, so if we have f of, what is x plus 8, or I guess in our case it'll be t, right?
Yeah, I guess you're right.
plus h. So what that means, this equals t plus h squared, okay?
So we
So we're
have
just,
t plus h squared
yeah,
minus, and then the other part of it was just f of a. So that would just be t squared,
yep,
right?
you're right.
And then we have an h on the bottom.
Okay,
Okay.
so
So
looking good so
now,
far.
yeah. So now we'll just have to do a little bit of algebra, right? So I'll just say this equals, we still have the limit part that is an L and an I and then an M, okay?
Okay,
As h approaches 0. Uh, we'll have t squared plus 2
2ht,
t h t or th plus
the, the,
h squared minus t squared. And this is all going to be over h. Okay. Now let's figure out what can cancel each other. Boom, that and that, right?
what and what, Jaden?
T squared minus t squared cancel each other out.
Okay, yeah.
Is it lagging on your screen a little bit?
Dude, did you write something? Because nothing's showing up.
Yes, I have written stuff.
There, well, no, there we go. Now it just finally showed up.
Well, this
Okay.
is not cool.
I mean, most of it showed up, just those crosses out didn't show up. So I don't know what the issue was there. Okay.
Okay.
Um,
But anyways, now we're doing this limit part as h approaches 0. Okay, so we can plug in. Well, hold the phone, Kip. I jumped the gun a little bit. We can
yeah,
actually
you did.
simplify this a little bit.
Yeah, you
I
can.
can cancel out some of those h's, right? I crossed out the 2 as the exponent because I crossed out one of them. Okay,
Right.
now we can take the limit as h approaches 0. So this term right here, that becomes a 0. Right,
Okay.
so what are we left with? We are left with the derivative equals 2t, because this is a big 0. Boop.
Right. Cool, Jaden.
I
So,
do.
dude, you did pretty darn good. That's what I would have guessed it was. So you did good.
Me too.
Um, so for all of you guys that didn't understand that part of the math, that's okay. Um, that's the definition of a derivative. And when you take an actual calculus class, they'll make you do this like 2 or 3 times, and then they'll say, "Hey, guess what? A lot of people have already done this, and they've found out shortcuts for you, so that you don't have to be the one doing the shortcut, or you don't have to do all this. Someone's done all the work, and they've given us a shortcut." Um, and so the first shortcut that, Jaden, do you want to briefly go over tonight, and we'll go in more depth probably at the start of next week. And do you want to use it to find the second derivative or the acceleration?
Sure. So the first like shortcut that we can introduce is like derivatives of polynomials that have powers, right? So in our situation here, we'll take the first
Hold on,
derivative.
Jen, we have a question. It says, so if h is approaching 0, then that out h as 0 in the equation.
Yeah.
Yes, kind of. I mean, yes.
After we have to simplify it because at the
Right.
beginning we have an h in the denominator and you cannot divide by 0. So that's why we had to go through several steps to kind of get rid of the h in the denominator, then we were able to take the limit as h approaches 0.
Yeah, right. You have to do kind of a whole bunch of different things mathematically, and then you can plug in the 0, right? But you try not to think of it as just plugging in 0, but it's as it approaches 0.
Yeah. Okay. So our first shortcut, just the power rule. If we have our original function as a polynomial t squared, the derivative is d prime of t. That's how you would say that. And you would bring the exponent out front, so the current exponent out front, and then you would keep the variable and then take that exponent and minus 1. Right? So then we end up with 2t to the 1, and anything to the first power is just that variable. Okay.
Oh, we got the same thing.
Yeah. Using the definition of the derivative is obviously a lot more work than doing this simple shortcut. Now, if we were to take the second derivative, it would look like d double prime of t. You bring that exponent out front, it becomes multiplication 1 times 2 t to the 1 minus 1. And that becomes 2 to the t of 0, and something to the 0 power equals 1.
And that's
So
mathematical. Remember that. 1, 0 equals 1.
So we just get 2 times 1, which is equal to 2. So our velocity would be this here, 2t. Our acceleration is a constant, which is 2. And our displacement is up here at our original equation.
And that is what we guessed, right, from our graph, right? We had this graph of velocity, and it had a slope, and the slope was constant throughout the whole thing, so it makes sense that our acceleration would be constant like we graphed. So there you guys go. That is your crash course into calculus and starting to get a little more in depth into physics.
Yes.
So next week, Jaden and I will be doing the opposite of derivatives, right? Which are called integrals. And we'll be starting from acceleration and working back up to displacement. And we'll be using that to derive some very, very important equations that physicists use all the time. So if you like this video, please don't forget to like and subscribe down below. And please tune in next week to learn about the opposite of a derivative, the antiderivative. Antiderivative.
Ooh.
And also, like always, we're going to leave you with some homework. And that's going to be try to find things that have limits. I'll give an example really quickly. Think of something round like this cup. Can you keep breaking down this cup into tiny and tinier little lines until it becomes actually round?
Yeah.
Does that exist? Is an object actually round? Do we believe that? Is it possible that it's actually just a whole bunch of tiny straight lines? And that's how animation works, right? You can just keep adding more and more vertices to try to make things look more and more round. Computers have no way to make a perfect circle. It does not exist.
Ooh. That's pretty cool, Kip.
That was cool. So,
all
thank
right.
you. We have a comment saying, well done, men. So, we did good, Jaden. High five.
Beep.
And we have a comment that says, did I miss anything? I'm not sure. I don't know when you started watching, so I can't tell you whether or not you missed anything.
Did
Yeah.
I miss it?
Also, anyone watching, if you guys have any friends that you think would enjoy this, please let them know. Our knowledge is here for everyone to learn. So maybe you didn't enjoy it a ton, but maybe you know someone who's struggling and could use some help. So there you
Yeah.
go. Thank you and good night. Jaden, anything you want to add?
I don't know if you mentioned this, but Thursday we are doing the help
I
stream.
didn't.
So if you are in need of help with answering any calculus or physics questions, or if you know of anybody, Thursday at 8 o'clock we'll be answering questions. So send them our way.
Okay.
Okay.
Thanks. Thanks and good night, all. Sorry, I spaced out there for a second. Science rules. Ooh, I need an animation that says that. You think I'll get in trouble?
You could spell rules ROOLS.
Yeah.
Rules.
Maynard James Keenan can make a perfect circle. I'm not sure who that is, but good for them. And I don't think they are a computer.
Even a protractor doesn't make a perfect circle, but
How do you know, Jaden?
because I measured 12 times. Just kidding.
Because it's physically impossible.
Yeah.
Because you can never make something perfectly round.
Yep.
So our
Okay.
life is a lie. All circles are approximations.